BP Shravani USN 1VE23CA009 branch CSE AI semester thoughts and post title operating system course code PCS 303 deadlock in operating system. Introduction to deadlock. Deadlock is a situation in a multitasking environment where two or more processors cannot proceed because each is waiting for the another to release resources. This condition can severely impact system performances and resource utilization. Understanding deadlock is crucial for developing efficient operating system and applications. Deadlock condition occurs when four necessary conditions hold simultaneously. uh, Mutual exclusion, hold and wait, no permission, and circular wait. Mutual exclusion means that resources cannot be shared among processors. The hold and wait condition allows processor to hold the resources while waiting for additional ones. Mutual execution is a condition where at least one resource must be held in a non shareable mode. If another process requests that resources must be delayed until the resources is shared, this condition is essential for deadlock to occur. Hold and wait. Hold and wait occurs when processor hold at least one resource is waiting to acquire additional resources. This situation leads to a scenario where processor are waiting identifiably for resources to be freed. Avoiding this condition is vital to prevent deadlock. No preemption means that resources cannot be forcibly taken from a process holding it. If a process is holding a resource and requests another one, it must wait until it voluntarily releases the held resources. This lack of preemption is a critical factor in the formation of deadlock. Circular wait forms a closed loop of processes where each process is waiting for a resource held by the next process in the loop. This condition creates a situation where no process can proceed, leading to the deadlock. Breaking this condition is necessary to dissolve or prevent deadlocks. Deadlocks prevention strategies. Deadlock prevention strategies aim to eliminate one of the four necessary conditions for deadlock. Techniques include ensuring mutual execution, avoiding hold and wait, enable preemption, and eliminating circular wait. By applying these strategies, the system can significantly reduce the likelihood of deadlocks occurring. Deadlock avoidance allows the system to make a resources allocation decision that ensures the system remains in a safe state. The Banker's algorithm is a well-known deadlock avoidance method that assesses resources requests before granting them. This approach requires knowledge of maximum resources needs in advance. Deadlock Deadlock detection involves periodically checking the system for deadlocks and taking appropriate action if one is found. The system maintains a resource allocation graph to track the allocation and request states of each process. If a cycle is detected in this graph, a deadlock is present and recovery measures can must be implemented. Recovery from deadlock. Once a deadlock is detected, the system must take action to recover from it. Recovery strategies must include process termination, resource preemption, or rolling back processes to be a safe state. The choice of recovery method often depends on the system's requirements and source availability. Deadlock prevention techniques. One common technique for deadlock prevention is the wait die scheme, which includes timestamps to manage resources request. In this scheme, older transaction can wait for younger ones, but younger transaction requesting resources held by older ones are aborted. This method helps to avoid a circular wait condition. Deadlock avoidance technique. In deadlock avoidance, the system uses algorithms like the Banker's algorithm to evaluate resources request. The algorithm checks whether granting a request would leave the system in a safe state. Keeping track of resources availability and maximum needs is crucial in this approach. Real world example of deadlock can be observed in a database system where transaction may hold locks on resources. For instance, two transactions may lock different rows in a table and wait indefinitely for each other to release their locks. Operating system managing multiple processes can also suffer from deadlocks if resources allocation is not carefully controlled. Case study database deadlocks. A common case study involves two transactions in a database where each transaction logs resources needed by the other. The scenario illustrates how deadlock can arise in a system that requires strict resources management. Understanding this case helps developers implement strategies to avoid such conditions. Tools for deadlock detection. Various tools and algorithms exist for deadlock detection, such as wait for graph and resources allocation graph. These tools help monitor resources allocation and identify cycles that indicate a deadlock. Effective use of these tools can streamline the process of detecting resolving deadlocks. Performance implication. Deadlocks can lead to significant performance degradation in operating system as resources remain locked and processes are stalled. The overhead of deadlock detection and recovery can also strain system resources. Therefore, minimizing deadlock occurrence is essential for maintaining optimal system performance. Optimal case study. Operating system. In operating system, processes may request resources in an unpredictable manner, leading to potential deadlocks. Case study in Unix and Windows illustrate how different systems handle deadlocks. Understanding these case study helps improve system design to migrate deadlock risk. Future directions. Future research in deadlock management may focus on machine learning techniques to predict and prevent deadlocks. Additionally, the development of more sophisticated algorithms for real-time system is crucial. Continuous innovation in this area can lead to more responsive and relatable operating system. Summary of key points. Deadlock is a crucial issue in operating system characterized by processes waiting identify for resources. Understanding the condition necessary for deadlock as well as prevention and recovery techniques is essential. Ongoing advancement in deadlocks detection and management will enhance system reliability and performance. Thank you.